Example 4, we've got p to a p a p squared and q to a q a q squared, right? And they're both points on the parabola x squared equals to 4ay. The tangents at p and q meet at r, and r lies on the parabola x squared equals to negative 4ay. Part 1, we want to show that r has coordinates given by a, brackets p plus q, comma apq. So if we get started first, right, let's check out a diagram and see what's going on. So we've got the parabola x squared equals to 4ay, and we've got p and q as two random points on the parabola. Okay, and we've got a tangent at p and we've got a tangent at q, and we know that the two tangents are going to intersect at r. So the first thing that we need to do in order to find the intersection point r is to find the equation of the tangent at p and the equation of the tangent at q. So that's something that I'm going to skip because I've done that numerous times before already. So to start, okay, the proof for the tangent at p to a p squared obviously starts off with dy dx. After you've got the gradient, just go with y minus y1 is equals to the gradient times x minus x1. And that's going to give us the equation y is equals to px minus ap squared. And from this, we can then say, of course, that similarly, the tangent at q to aq, comma aq squared, right, is going to be given by y is equals to qx minus aq squared, right? So if I want to find the coordinates of r, I'm just going to take these two equations and I'm just going to solve them simultaneously. So solving for r, okay, so what that's going to give us, if I equate the two, while looking at px minus ap squared is equals to qx minus aq squared. And of course, this whole process should be very familiar to us because I've done this a number of times in previous examples already. Okay, so here what I'm going to do is obviously just rearrange, move the qx to the left. So I've got px minus qx, which is going to be p minus q, lots of x, is equals to, move the minus ap squared to the right. So I've got ap squared minus aq squared, which is a brackets p squared minus q squared by difference of two squares becomes p plus q times p minus q. And here we can cancel the p minus q away, right? And that's going to leave us with x is equals to a brackets p plus q. And now once we've got this, and if we want to find the y value, we'll just take this and we just substitute it back into either of the two equations. Okay, so part 1 continued when x is equals to a brackets p plus q, right? Remember that the equation of the tangent at p, which is my preferred one, is given by px minus ap squared. Of course, if I take this and substitute it into the equation of the tangent at q, we'll get exactly the same thing. It makes no difference. So here, if x equals to a brackets p plus q, my y value is going to be given by p times a brackets p plus q minus ap squared. And if I expand the whole lot, this gives us ap squared plus apq minus ap squared. And we know that ap squared minus ap squared disappears. So my y value is therefore just apq. And now putting everything together, this shows that the coordinates for r is therefore given by a brackets p plus q, comma, apq. And that's all we have for part 1. Okay, so now that we've got the coordinates of r, okay, so that's going to be this point over here. If I come back to the question, part 2 wants us to show that p squared plus q squared plus 6pq is equals to 0. Now this condition has to come from somewhere, okay, and the information that leads to this condition has to be given in the question. So if I come back to the question, right, we've got the 2 points on the parabola. We've looked at the tangent at p and the tangent at q, and we have solved for the coordinates of r. So everything up until this point in time has been looked after. However, the second piece of information over here tells us that r lies on the parabola x squared equals to negative 4ay. So we haven't quite looked at that yet. Okay, and this is going to be extremely important because in terms of the locus of r is a variable point. Normally speaking, p and q being two variable points on the parabola, okay, which are free to do whatever they want, they can be wherever they want, and as a result, the intersection point between the two tangents r can be wherever it wants. So everything's very chaotic. But now what happens is now I'm coming along and saying that, okay, p and q can still vary, okay, they can still move around, but we want to force the movement of p and q such that when they intersect or when their tangents intersect, okay, the intersection point of R is always going to lie on the parabola x squared equals to negative 4ay. So if I know that the tangent has to intersect on x squared equals to negative 4ay, then with the coordinates for R, which we just solved for, this point for R, which is given by a brackets p plus q, comma, apq, if R always lies on x squared equals to negative 4ay, that means that the coordinates of R must satisfy this equation. Okay, so if I use this condition algebraically speaking, okay, so part 2, if I say that R, which is given by a brackets p plus q, comma, apq, lies on x squared equals to negative 4ay, then what we can say is that a brackets p plus q all squared is equals to negative 4a times apq. Okay, because the coordinates must satisfy the equation of the curve it lies on. So if that's the case, expanding this, I've got a squared, p plus q squared is going to become p squared plus 2pq plus q squared is equals to negative 4a squared times pq. And if I expand the whole lot, or rather if I divide both sides by a squared, I think that's going to be a little bit easier. So if I divide both sides by a squared cancels off, and it's okay because a is just a constant that is not equal to 0. And what we've got right now is p squared plus 2pq plus q squared is equals to negative 4pq. And if I move negative 4pq from the right to the left, we've got p squared plus 6 times p times q plus q squared is equals to 0, right? That's what we have for part 2. That's a condition, right? This condition tells us how p and q are interrelated, because when we come back to the question, okay, with this diagram over here, okay, now R is forced to lie on this parabola down here, x squared equals to negative 4ay, okay? And it's a condition that links p and q together in the sense that if p is here, it forces q, okay, to be here such that the tangents intersect somewhere on the curve. If I move, for example, p over here, then you guys can see that I must move q somewhere in turn, okay, so that the tangent drawn at that point is also going to intersect on the parabola x squared equals to negative 4ay. So in other words, what this is saying is that once we've got a specific point for p, right, p is free to wander, but if we say, okay, p has to be here, once we've got the position for p, q can no longer be wherever it wants to be. Okay, once we fix p, q becomes fixed as well, such that the two tangents will always intersect on the parabola x squared equals to negative 4ay. Okay, so the 2 points cannot wander wherever they want to be. Okay, instead, what happens is that the 2 points are going to move relative to each other. So if p is at a specific point, q has to accommodate for the position of p, and q becomes fixed relative to p. And once we have that, that's going to ensure that R is no longer chaotic and that it actually lies on x squared equals to negative 4ay. Now that being said, part 3, if we come back to the question, okay, just the last part of the question, as p and q vary, we want to show that the locus of the midpoint of the chord PQ is on the parabola 3x squared equals to 4ay. So if I take P, right, so part 3, which is given by 2AP, comma, AP squared, and Q, which is given by 2AQ, AQ squared, then we know that the midpoint, okay, so let's say M is the midpoint of PQ. The midpoint of PQ is going to be 2AP plus 2AQ over 2, comma, AP squared plus AQ squared over 2. So with the 2AP plus 2AQ over 2, we should be able to see that this is going to become just AP plus AQ, which is A brackets P plus Q. And the AP squared plus AQ squared over 2, that's just going to become A over 2 times P squared plus Q squared. So with the parametric equations of M, right, where X equals to A brackets P plus Q, and Y is equals to A over 2 P squared plus Q squared, right, we know that this is a 2-parameter type locus problem because we can see that there's P and Q in both the equations. Now, when we're looking at something like this, okay, so say X is equals to A brackets P plus Q, and y is equals to a over 2 p squared plus q squared. If this is the only thing that we know, it's actually impossible for us, okay, just by these two equations, to eliminate both parameters at the same time. So, well, by impossible, I mean like 99% chance that we're not going to be able to do it unless it just coincidentally works out extremely well. But when we look at this, I mean, if you think about it, to demonstrate, I know that x and y are related, right? I mean, when we look at y, we've got the p squared plus q squared. So if I look at how x is related, I can say that from x on a is equals to p plus q. So if I want p squared plus q squared, that's obviously going to be related to the x on a equals to p plus q, and I'm going to square both sides, right? So if I square both sides, I know that x squared over a squared is therefore p squared plus 2 times pq plus q squared, right? And over here, if I say that, okay, 2y over a is equals to p squared plus q squared, and then if I substitute this in, you guys will see that I won't be able to get rid of the 2 times p times q. So when we're dealing with two parameter type locus problems, what we always need is we need that extra condition. Okay, in this case, the extra condition is given by the fact that we're forcing R to lie on the parabola x squared equals to negative 4ay. And like I was saying earlier, that forces P and Q to move in a certain fashion relative to each other, so that P and Q are not free to vary off by themselves. If they are free to vary off by themselves, then there'll be no pattern available for us to kind of like work on. But since we did force R to lie on the parabola x squared equals to negative 4ay, everything becomes more ordered, and the condition that comes out of that was p squared plus 6pq plus q squared, right, is equals to 0. So in other words, I can kind of use this condition, okay? This condition is a universal truth for us right now. So if I say that p squared plus q squared is equals to negative 6pq, right? Then in this case, I can say that x squared over a squared is equals to p squared plus q squared is negative 6pq. Negative 6pq plus 2pq is negative 4 times p times q. And with a 2y over a equals to p squared plus q squared, right, I can say that 2y over a is equals to negative 6 times p times q, and everything becomes very nice. Okay, I mean, over here, I can simplify things further by dividing both sides by 2. So y over a is equals to negative 3pq, for example. So if I take this as equation 1, this as equation 2, up to you guys how you want to work with 1 and 2 at the same time, right? But if I divide both of them, okay, or I can make PQ the subject and then substitute it into the other. It doesn't really matter by this point in time. But if I take equation 1 divided by equation 2, I've got x squared over a squared over y over a is equals to negative 4pq divided by negative 3pq. So the pq's cancel and the minus sign cancels, right? So in this case, I can then say that x squared over a squared over y over a, if I multiply the top and bottom by a squared, that tells me that x squared over a y is equals to 4 over 3. And of course, with this equation over here, if I just cross multiply, you guys can see that my final Cartesian equation is given by 3x squared is equals to 4ay. And this is the equation of the locus of the midpoint of PQ as P and Q moves wherever they want, okay, restricted so that the intersection point of the tangent, right, always lies on x squared equals to negative 4ay. This is the locus of the midpoint of PQ as P and Q varies. Okay, so that being said, this concludes example 4, our first look at a two-parameter locus type problem. Okay, and remember that with two-parameter locus type problems, we always need a condition to help with a simplification.